Welcome to Math 63, Unit 2, Lecture 2, Part 1, Discovering the Exponent Rules. Now that we've done some simplifications, let's try and write down what our rules are for how addition and multiplication work. Okay, so let's start with the rules for addition. For multiplication, we have the same rules, actually. So we have these rules about how addition works and about how multiplication works, but how do they interact together? And that's the distributive law that we mentioned. Both addition and multiplication together. That's the distributive law. Now, the next step up, right? We had addition, which we understand. We have multiplication, which is repeated addition, is one way to think of it. The next step up is exponentiation, okay? Right, we know that things like a to the power of 2 is just a times a, just like 2a is equal to a plus a, right? So there's that as well going on here. So the relationship between exponentiation and multiplication is going to be kind of the same as the relationship between multiplication and addition. Okay, so let's see what I mean by that. Well, what are the rules that we've got? If I have, let's try and look at the distributive law, but instead with exponents. So I had a times b plus c. Let's take that plus and turn it into a multiplication. So bc. And now, rather than multiplying, I'm going to use an exponent. Okay, so we've taken the b plus c, turned that plus into a multiplication here, and we've turned the multiplying by a into exponentiation. And we should find that this rule kind of still works. So what we get is b to the power of a plus c, sorry, not plus, because plus turns into multiplication, right? So we have b to the power of a, c to the power of a. And in fact, that is true. If I had something like x times y to the power of 3, right, I could write that as xy times xy times xy, and then through the commutativity of multiplication, I could say, oh, this is x times x times x times y times y times y, and so I've got x cubed, y cubed. So it does work. Okay, cool. How many of these other things work? What other properties do we have for exponents? Well, let's check some things. Do exponents commute? Can I say 2 to the power of 3 is equal to 3 to the power of 2? Well, check. 2 to the power of 3 is equal to 8. 3 to the power of 2 is equal to 9. So these are not equal. So exponents don't commute. All right, we can't do it that way. Are they associative? Well, it doesn't look good if they don't commute, but let's try. Let's try 2 to the power of 3 to the power of, let's go with 4. Okay, so we'll start looking like that, and then we'll also try 2 to the power of 3 to the power of 4, like this. So we have two different ways of forming power towers. This one here is 8 to the power of 4. Over here we have 2 to the power of, 3 to the power of 4. 3 to the power of 4 is 81. This one here ends up being, let's get out the calculator. Okay, don't use your phone on a test, but here's a calculator for us. 8 to the, scientific. Okay, so 8 to the power, 8 to the, there it is, back up, 8 to the power of 4 is 4,096, okay? And what's 2 to the power of 81? 2 to the power of 81 is a ridiculously large number. They are not equal to each other at all. Okay, so exponentiation is not commutative, it's not associative. But we do have some of the properties from multiplication and addition shining through. So I've shown you one here where we're able to distribute across. Now let's try a similar thing using the distributive law. Let's see if we can come up with another rule. I'm going to need a little bit more paper here. Okay, so another rule that we could use, we could try the distributive law but reading it the opposite way. Okay, so a times b, we're going to turn that into exponentiation, but rather than a being the exponent, let's make b be the exponent, right? Because since it's not commutative, a to the power of b is different than b to the power of a. So let's try this. A to the power of b, and then plus turns into a times, a to the power of c. Okay, so what would this end up being? All right, this ends up being a to the power of b plus c. Okay, so what happens here, right? Well, let's try to demonstrate this using some numbers, shall we? Let's go 2 to the 3 times 2 to the 5. Okay, well, if I write that out long form, it's 2 times 2 times 2, and then times 2 times 2 times 2 times 2 times 2. And we can count all those up to get 2 to the power of 8, which is 2 to the 3 plus 5. So that rule does work too. So we've got that rule, we've got that rule. Okay, what other rules can we come up with based off of what we've done here? What if, well, let's think about this. Hang on. Okay, I've been looking at the associativity of multiplication here, and it's got me thinking. What if I were to write a to the power of b to the power of c like that? What does that end up becoming? Well, if we follow here, then it should be something like a to the power of b times c, right? Because if we turn this multiplication into an exponentiation, and this multiplication into an exponentiation, then this becomes an exponentiation somehow, maybe, kinda, I don't know. Let's see if that does work though. Let's test it. So let's go with, I don't know, we'll go with 3 squared to the power of 3. Okay, so that's the same as saying 3 squared times 3 squared times 3 squared. And we know from our work before with this rule that I can just add my exponents. So this is now 3 to the power of 2 plus 2 plus 2. Okay, so that is just 3 to the power of 2 times 3, which does demonstrate that this rule is true. So there we go. So we have another rule. So if we have an exponent of an exponent, we can multiply our exponents. Let's see if we can come up with other rules. Okay, here's one that I just thought of. With the distributive law, we could have, instead of talking about addition, we could have talked about subtraction, and it would be just as true. So that implies to me that rather than talking about multiplication, we could talk about division. So let's say this is instead a division. So we have b over c to the power of a, and turns out that that is indeed b to the power of a over c to the power of a. And if you want some evidence, right, for that. We could try 2/3 to the power of, I don't know, let's keep it easy with 3, right? And so that's going to be equal to 2/3 times 2/3 times 2/3. And we know that with multiplication, we just multiply across the numerators and multiply across the denominators. So this is 2 cubed over 3 cubed cubed. And so there we go. We've shown that exponentiation does in fact distribute across a division or through a fraction like this. All right. What about if I had, let's move on down here to this one. What if I had a to the b divided by a to the c? Well, it turns out that dividing by an exponent with the same base is going to turn into subtraction in the exponents. Okay, let me just erase this to give me some room here. So let's see if that's the case. So if I had 2 to the 5 over 2 to the 3, right? Okay, so that's going to be, I mean, that should be 2 to the 2, but let's see if that's true. Right, so we have 2 times 2 times 2 times 2 times 2 all over 2 times 2 times 2. Okay, so I could divide numerator and denominator by 2, and then by 2, and then by 2, leaving me with 2 times 2, which is 2 squared, which is 5 minus 3. Okay, so that works. So we've got 2 more exponent rules there. Okay, so far that gives me 5 nice exponent rules to work with. Exponents distribute both across multiplication and across divisions. Okay. Also, if you have a base that is the same, all right, there's kind of this sort of weird distributive thing, but rather than distributing, it doesn't feel so much distributing, what happens is the exponents will either add or subtract depending upon whether we're multiplying or dividing. Okay? Also, we know that if we take exponents of exponents, then our exponents will multiply together, and we'll get b times c like that. Okay. Anything else that we can think of? Let's think. Okay, so I've rewritten our list of rules. We've got these 2 pairs, talking about distributivity here, and talking about how exponents can combine by adding or subtracting depending on whether we're multiplying or dividing. So I know that. And there's this, I've paired them up because this is just taking a multiplication and saying, well, what happens if it's division? And this is saying the same thing, taking a multiplication and saying what happens when it's division. So let's look at this one here now, and is there a way that we could take a multiplication and turn it into a division and get a new rule? Well, the only multiplication that's going on is right here with b times c. So what if I were to turn this into a to the power of b over c? Well, just following this rule, this should be a to the power of b to the power of 1 over c. Now, I don't know if that is useful yet. How could we come up with something to make sense of this? Well, what this could do is tell us, this could give us a way of defining what exponents that are fractional really mean. If I have an exponent, like, I could ask the question, hey, what is 4 to the exponent 1/2? Okay, well, I don't know. But I could try and figure it out based off of what I've got here. 4, I know, is 2 squared, so I'm going to write this as 2 squared to the exponent 1/2. Okay, now following the rules, either one of these, this is going to be the same as saying 2 squared times 1/2. Sorry, not squared, 2 to the power of 2 times 1/2. There we go. So 2 times 1/2 is 1. So this is 2 to the power of 1. 2 to the power of 1 is 2. So 4 to the 1/2 is equal to 2. Okay. And so what this is telling us, I mean, hopefully you're seeing this, putting something to the power of 1/2 is taking something that's a square and getting rid of the squaredness and just taking the square root. So what we've got now is this new rule from this idea here. A to the 1 over n is equal to the nth root of a. Okay, I'm going to erase this now so that I can keep everything clean. Okay, so that gives me another rule. All right, so we have 1, 2, 3, 4, 5. This is kind of half of a rule. So we've got about 6 rules so far of exponents. If I have fractional exponents, okay, I know what to do with those. But what about negative exponents? Nothing here seems to make clear what negative exponents would be, but let's take a look at, here's a place where negativity shows up, right? Where we've got subtraction. So maybe I can figure out what goes on with negative exponents based off of this. Okay, let's say I had something like 3 squared over 3 to the power of 4. Okay? Based off of what we've figured out here, this should end up being 3 to the negative 2. Okay, but what does that mean? Well, 3 squared over 3 squared over 3 to the 4, well, we could do some cancellations. I could divide numerator and denominator by 3, so that would get me 3 to the 1 over 3 to the 3, and then I could divide it by 3 again to get 1 over 3 squared. So what I'm seeing now is 3 to the negative 2 is equal to 1 over 3 squared. Okay, so notice there's a 2 here and a 2 here. So if I have a value, let's say a to the negative n, that will equal 1 over a to the n, based off of what we did here. Okay, so I've got fractions, I've got negatives, I know about positives, but what about 0? Okay, well, 0 is probably the simplest rule to remember. And once again, we're going to use this rule to figure it out. If I have a to the power of 0, I could think of that as a to the power of, pick any of your favorite numbers. Let's say a to the power of 5 minus a to the power of, minus 5. 5 minus 5, let's say. So that's the same as, just read this backwards, a to the 5 over a to the 5. Well, that's the same, that's a number over itself, so that must be 1, has to be. All right, so a to the power of 0 is 1. So no matter what a is, if I put it to the power of 0, I will get 1, so long as I am able to divide by a. So there is one thing that I'm not allowed to divide by, as many of you are aware, right? So 0 to the power of 0 is the one thing that we go, no, don't do it, don't do it. Okay, so this does not necessarily, well, this doesn't equal anything. 0 to the power of 0 is what we call an indeterminate form, and we just go, let's not talk about that right now. Okay, so that's how we're going to handle that. Okay, so those are our exponent rules. We have anything to the power of 0 is 1. We talked about negative exponents, that just reciprocates things. We talked about fractional exponents there. We've got exponents of exponents turns into multiplication. We've got, if you have the same bases, the exponents either add or subtract, depending whether you're multiplying or dividing. And we have, if you have an exponent of a product, then the exponent can distribute, or if you have an exponent of a quotient, meaning a division, then the exponent also distributes. All right, there's our rules. That's how exponents work, okay? And using all of this, we can do all sorts of good work with exponents.